Welcome back. In this video, we'll discuss section 17.4, the central limit theorem. The primary question we want to investigate is this: when can we use the normal model to model the sampling distribution of the sample mean? So if you recall, we're working with a quantitative variable. The example in the last video involved this collection of 1,000 pennies from which we were taking samples. And the variable was the age of the penny. So for our sample, we were computing the sample mean age. It turns out we can use the normal model if the following assumptions and conditions are met. So we need to check this independence assumption, which says the sampled values must be independent of each other. Now we end up checking a couple of conditions for the independence assumption. One is the randomization condition, which says observations need to be collected with randomization. And the other condition is the 10% condition, which says the sample size n should be no more than 10% of the population. Now we also need to check the sample size condition, which isn't a hard and fast rule, it's more a guideline of n greater than or equal to 30. So we want the sample size to be at least 30, unless the population is very non-normal, in which case you might need an even larger sample size. Instead of relying on simulation like we did in the last video, we have an important theoretical result about how sample means vary. It's called the central limit theorem, which I'll abbreviate CLT for a sample mean. It says when a random sample is drawn from any population, and pay attention to the wording here, it says from any population. I'll have more to say about this in a moment, but what it's referring to is the shape of the population can be anything at all. Might be fairly symmetric, but it might be skewed as well. The sampling distribution of the sample mean y bar will have the following properties. We're able to comment on three things: shape, center, and spread. In terms of shape, the distribution will be either normal or approximately normal. I'll have more to say about that in a moment. For center, the mean will equal mu, where mu is the population mean. And for spread, the standard deviation will equal sigma over the square root of n. Here, sigma is the population standard deviation, and n is the sample size. Now, if the population itself is normal, then the shape of the sampling distribution will be exactly normal, and it doesn't matter what the sample size is. If the shape of the population distribution is, say, skewed to the right, as we saw with the collection of pennies, then the shape of the sampling distribution will be approximately normal, and the approximation is better with larger sample sizes. Here's the table we filled out in the last video. So this was for that collection of 1,000 pennies. If you think of the 1,000 pennies as your population, we saw that the mean age was 12.264 years. The standard deviation was 9.613 years. And the shape of the population is skewed to the right. Now, what the central limit theorem says about the standard deviation of the sampling distribution is that it should be equal to sigma over the square root of n. Here, sigma is the population standard deviation, 9.613. N is our sample size, and if we're considering a sample size of 50, we end up with this, 1.3595. We can confirm that this value that the central limit theorem predicts for the standard deviation, 1.3595, is reasonably close to what we saw in our simulation. When we had a sample size of 50, the standard deviation of sample means was 1.354. Anyway, we'll stop there for now. See you next time.